I'll wait for the crowd. Hello, hello. There you are. Welcome. I need to position this a little better. Somehow. Hello, hello. Check, check, 1, 2. Okay. Alright, so I got one viewer. Welcome. This will be for everybody that watches this, but I want to show you what I got, and then I'm going to show you what I'm doing, and then I want to ask some questions. Now let's make this other one bigger for a second. So this is a simple concept, but it's quite an interesting idea. So I've got two capacitors here. These are supercapacitors. They are of this type, 2.7 volt, 4.7 farads. So they're decent size. Then I've got a digital multimeter. I've got a current probe that will measure the inrush current. I've got the oscilloscope for measuring voltages, and then I've got a light bulb here. The light bulb is the key in this, because the light bulb is going to light up. Imagine that. Okay, kind of would like this camera a little closer, but maybe I'm actually going to set this over here. Kind of want it to be close. Alright, so here's what I'm going to do. I'm going to charge up one capacitor. Oh, by the way, the grounds on the capacitors are connected together. I think I'll show you that. So the grounds are connected together, and the positives are hanging open. So this is split the positive. That's what I'm doing. Splitting the positive. It's an interesting concept. Okay, so what I'm going to do is I'm going to short out one of the capacitors. Actually, this thing's this thing's been charging. So what I'm actually going to do is I'm going to short out both of the capacitors just so they're both at ground state. So channel 1 on my oscilloscope, I'm sorry, the blue one, channel 2 at the top is the charged capacitor. Channel 1 is the uncharged capacitor. Channel 3 is the current probe, which isn't real important right now. Really, this digital meter is actually kind of more important than anything. Maybe if I put it here you can read it. Maybe not. There, like that, maybe. Let's see if I can set this up against something. You can kind of read that. It says 0 milliamps right now. Alright, so you can see that both the capacitors are at 20 millivolts, or basically nothing. So what I'm going to do is I'm going to charge up one of the capacitors while the other one is still shorted. So we're going to let it charge up to about 2.5, 2.6 volts. I'm going to leave it there for I can't find my stopwatch. There it is. For about 1 minute. So that it's fully charged at this 2.6 volts. And what I'm going to do, I'll tell you what I'm going to do while we're waiting. I'm going to disconnect the power completely. You have to ignore the hammering in the background. I'm going to disconnect the power completely. Okay, and I'm going to short the capacitors together so that the energy is equalized across the two capacitors. Okay, easy test. We're not going to worry about the ammeter because it pulls quite a bit of current when you dead short the thing, right? Alright, that's about 1 minute. I'm going to disconnect this, which is the short across that one. So here we go. I'm going to short the two capacitors, the two positives together. Alright, and the voltage is going to equalize pretty fast. So you can see they've equalized at about 1.16 volts. Alright, 1.18, 1.16. That's fast, that's real fast. So they're pretty well equal. Okay, so now what I'm going to do is I'm going to short out the capacitor again, the one that needs to be at 0 volts. I'm also going to short out the one that's supposed to be charged so we can bring it down to nothing, just so it's at nothing, because we want to charge it back up again at the same amount of time, basically. Alright, that's probably good enough. Now we're going to charge up caps, the one cap. So I'm going to let it go for another minute. Now this time, I'm going to discharge, no, I'm not going to discharge anything. I'm going to connect a light in the place where I connected the short. And what's going to happen is the light's going to light up. And what we're trying to determine is if the voltage is any less than what it was when we had a dead short. Alright, coming up on a minute. So there's our minute. Same amount of voltage, same amount of charge time. I'm going to disconnect that short. Now we're going to connect through the ammeter the light bulb. So watch the ammeter if you can see it. Alright, so you saw the light up. It's still actually lit up. Now we're going to look at the voltage. Now, let's just wait because you got to see the milliamps. It's still pulling 75, 50 milliamps, and the voltage is not equal yet. It's still equalizing, of course. 25 milliamps. Milliamps. 9, 8, 7, 6. Okay, it's pretty well, it's at 5. It's still going. But now we have 1.8 volts. So the dead short actually pulls a lot more current when you short the positives. It actually pulls a lot more current and basically wastes the energy in the wire transferring to the two positives. However, we can also put a load there instead of a short. And the higher resistance actually allows for the energy to be transferred a little slower. So we had no losses between lighting up the light bulb and the dead short. Actually, the dead short theoretically lost more voltage because it was a short and not a slow voltage transfer. So what this means is that we didn't consume any electrical energy during the transfer, but we were allowed to use the voltage that had to be the current flow basically between one and the other in a load. So the system is equivalent of basically zero waste power transfer. So it's kind of hard to decipher. It's kind of a hard one to look at because you got to remember you're just moving electrons, or if you want to look at it that way, you're just moving. You have current flow from one place to another that you have potential difference you can use, but there's no losses there in that transfer, even though you're lighting up a light bulb. So you're putting out photons. You're admitting energy from the system, but yet you're not losing any energy during the transfer. No matter what you do to transfer it, you're going to consume X amount of power. Anyway, that's all. I was just messing around with this simple idea. Considered split the positive. And that's all I wanted to show you. I don't think I need to do it again. I could if I really wanted to. I don't see why I need to though. So we can short this guy. Charge these back up. So what is that? 1.6 volts. So if we put a resistor there, of course, the energy is being consumed. So some could consider this a no-loss system, which I guess you got to think about the wire. I don't know, just something to think about. No claims here, just something interesting. So, for those of you who want to start from the beginning, you can watch this video over. I'll do it again. So I'm disconnecting this. Got the cap shorted. You can see channel 1 is 40 millivolts. And I'm going to dump it. Doop. Big voltage spike, or current spike. And we're at about 1.4 volts, equal on both sides now. It's pretty fast. 1.6, 1.8, or 1.16, 1.16, 18. So basically, the energy is just being wasted during the transfer. Because let's do this. Here's what's interesting. So we're charged up to 2.6 volts. 2.6. Okay. Half of 2.6 is 1.3. So there's still losses in this particular system, but the point is you can use that positive to positive transfer. The flow is actually kind of backwards if you think about it, because you're equalizing the voltage in parallel across the caps, but in the process also lighting up a bulb. So if we had no losses, we'd be somewhere around 1.3. So technically we've lost about 0.12 of a, well, actually be less than that because it's divided by the half. Somewhere around 0.1. Oh, I screwed that one up. I didn't disconnect the shorted lead. I'll do that again for you. My fault. I've done that plenty of times myself already. So we'll let this charge back up. So theoretically, the wire would be heating up and dissipating heat, where the light bulb is putting out light. Same probably amount of power, I presume, but useful work with the light, where the short and heat isn't really useful at this level. Alright, charged up. Take the short off this time. Now I'll hook the light bulb up. Now it's equalizing. It's very slow through that light bulb. The meter's going to turn off. So again, we should have 1.3, and we're at about 1.6 when it balances out. Oh. Shubis just texted me. At the dentist. Wish you were here. Okay, so we're at 1.6 volt, still pulling 2 milliamps, but that's it. So I'll leave you with that. See you later.